Okay, so we are recording. So with all of this, if you guys have specific questions or concerns over specific topics as we go along, please speak up. Let me know. I might not always see the chat, so just unmute yourself really quick and just say, hey, I have a question. So that way we can really go through what is the most helpful for you guys. Okay, that's the whole goal of this. So starting that, any specific questions or concerns that anybody has right now that they want to throw out there, so that way I can write them down and either answer them right now, or we can wait until we kind of reach that point in the material and answer them then. Okay. Again, if you have a question, you can always just throw it in the chat, and we will get to it as soon as we can. Okay, so we're starting off at the very beginning, the introduction to biochemistry and review of the basic chemistry concepts. First things first, the atomic structure. I'm going to fly through these pretty quickly, just because hopefully these aren't too new type concepts. So this is kind of a look to how I go about doing all of my material and everything, how I do. I love Google. I literally will sit here and Google 8 million things as I'm learning different subjects and Googling them and then putting them into your own words is one of the best ways to really test your understanding of everything. So for example, we took an atom. So it's the basic unit of a chemical element. But in all actuality, we don't actually know what that means, because chemical element can mean a whole bunch of different things. So we want to define that as well. So the chemical element is a part or aspect of something abstract. Blah, 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 blah. Chemical element. And I love these people always also ask questions. So it's any substance that cannot be decomposed into similar substances by ordinary chemical processes. So these are the most basic units of everything that is made up of everything. So basically the smallest units that make up everything in the universe. I can spell. There we go. That is the atom. The next question is the fundamental subatomic particles present in an atom are, should we have a proton, neutron, and electron. Of these, either in the chat or unmute, what are the charges of each of these different subatomic particles?
Hey, I don't know if there is a chat feature, but protons are positive, neutrons are neutral, electrons are negative.
Perfect. There is a chat feature. Usually, if you're on your computer, it's up at the very top left. You'll have show conversation, like a little chat button. If you're on your phone, I don't remember exactly where it is, but it should be there somewhere.
Drake, I'm sorry, I'm on my phone, but it says that I don't have an access to the chat. Like I can message, but I can see the messages.
I don't see either one. If I do open the chat, it just goes to like a separate chat,
thing?
I guess. Is there anyone not saying anything? Is that all? Well, is that the reason why maybe? No one just hasn't said anything?
Yeah, nobody's really said anything in the chat. Just there was just one thing when I
asked
I don't
even see people could hear me.
Okay,
so I don't know.
let's just unmute and talk then, because that's actually a little bit easier than having to type everything out in the chat. So when we talk about protons, neutrons, and electrons, specifically we talk about these when we're talking about atoms and we're talking about the whole periodic table and all of our different elements that we have. And what is it that makes defines like what an element is of
The atomic
these
number?
three. So the atomic number is going to be a little bit different because if so. I mistake. Again, this is going to be general chemistry. So yeah, you're correct. I was thinking mass number. Yeah.
Okay.
So yeah, sorry, my bad.
You're
so yeah, so
fine.
we have the atomic number, which is going to be the number of protons in the nucleus of an atom. And the whole part of this, the number of protons in it, is going to determine the chemical properties of that specific atom, kind of what it does, what role it's going to play in the buildup of everything. Neutrons are neutral. These can change depending on the atom. More or less, you're going to see they like to match kind of close to the number of protons, but it's not super important. Electrons, these are the two that we want to focus on, the protons and the electrons. So electrons, these are going to be outside of the nucleus of the atom in what we call valence. Well, there's two different theories of this. So what they'll be in what we call an electron cloud, and we will organize them into valence shells. Okay. Is there anybody who has a question about what I just wrote there?
No, that looks pretty easy.
So will it be defined as the
beginner.
electron cloud or the valence shells? It could be called either one.
So in the purpose of this class, we're going to focus on valence shells.
Okay.
That's going to be our main focus for the purpose of this class. The whole scientific community, this is something that's actually still like new research is coming out on understanding this. So it's within the past couple of years that they have actually discovered that there aren't technically valence shells like we think they are. But for the purpose of the level of chemistry that we need to learn here, we're going to go with valence shells. We're going to say that valence shells are the organization of the electrons, and they are the most important when it comes specifically to bonding. So the electrons going to be what are most important for bonding of different atoms together. Okay. So when we talk about a valence shell, you can imagine them essentially as these rings around the different around the nucleus of an atom. And there's a very specific order to the number of electrons that can fit into each shell. So for example, in the first shell, you get 2 electrons. In the second shell, I believe it is 8.
Up to 8? Yeah, I think it's up to 8.
Yeah. Let me just make this easy so I don't mess it up. The first shell holds 2, the second shell holds 8, the third shell holds up to 18. And that's about as far as we go in this class. We won't really go much further than that at all. And when we talk about the number of electrons that it's going to be holding, that's actually why the periodic table is set up the way that it is. So if we look at this, hydrogen, helium, the reason why it's all the way up here by itself is because the number of electrons is supposed to match the number of protons, or wants to match the number of protons. So the top row is the first shell. The second row, then 1, 2, 3, 4, 5, 6, 7, 8 is our second shell. And then 1 sec, let me double check this because I don't love. Okay, yeah. There's a piece that I'm missing here. I know that there is, but for the purpose of the class, it's not that important. So I'm not gonna do a tangent dive into to figure out exactly what it is that I'm missing, but it's fine. Yeah. So this is the first shell. We talk about this is the second shell, and all the way over here to the right, saying that these are going to have a full valence. Their last valence shell is going to be full, and that's what we want to understand the most. Is that atoms are going to be the happiest when their outermost shell is full. This means that they can either take in additional electrons to fill out that shell, or they will get rid of electrons to fill that shell, or to get rid of that shell. So the next lower one is full. This is why there was a quiz question that somebody brought to me asking about how many available electrons did oxygen have in order for binding. And so if we actually look at that, and we look at the periodic table, depending on which side of the periodic table that you are on, you're going to see exactly what happens. So if we have hydrogen, for example, let's say that we start with hydrogen. Here in the middle, there's one single. Normally that would have one valence shell and one electron to match. But because if it's less like, it doesn't want to necessarily take on another electron because that might be harder. So you typically hydrogen boots out an electron and you get a hydrogen with a plus on it, meaning that it doesn't have any electrons on it. Helium is going to have its 2 electrons and it's happy. All here on the side, lithium, beryllium, and boron are going to give up their electrons. So lithium gives it up, beryllium gives it up, boron gives it up. Carbon, this is why all of us are carbon-based life forms. It has 4 electrons. Rather than giving it up or taking more away from other people or from other atoms, it's instead going to want to make bonds with stuff. That's why like a ton of chemistry that we're going to go over all revolves around carbon. And us ourselves, we're carbon-based life forms for this reason, that they like to form these type of bonds. As we continue to this other side, nitrogen, oxygen, and fluorine, these ones are going to instead gain more electrons. So we'll often see, for example, oxygen, fluorine, their first shell will be full. And then that second shell will be almost completely full. Fluorine will just be missing 1. Just missing 1. And oxygen, sorry, this doesn't look super pretty, but I'm trying to go a little fast. And oxygen is missing 2. So if we're talking about how many spaces they have in order to form bonds, or how many bonds like they're able to form, oxygen is looking to form 2 bonds and fluorine would be looking to form 1. So these typically present kind of in the wild as an oxygen is a -2 and fluorine is a -1. And that continues down as well. So fluorine is a -1, chlorine is a -1, bromine is a -1, oxygen is -2, sulfur typically is -2, selenium is -2, and so on. Any questions about all of this so far?
Yes. So as we go forward, we'll just be able to like memorize which ones will be giving off electrons, and which ones will be accepting them.
Yeah.
And
And
then,
to be
go ahead. I'm sorry.
to be completely honest, in this class, in this biochem class, we're really only going to pay attention. Like 99% of what we're going to be doing is going to be, get my brush, is going to be hydrogen, sodium, potassium, calcium, carbon, oxygen, chlorine. That's like 99% of what you're going to see in your chemistry and physiology type classes.
Okay, and then you said carbon likes to make bonds. So does that mean it doesn't share the electrons? It only makes bonds, or it does still share depending on the situation?
It's going to share electrons, but it's not going to give up its electrons. So it will, when we'll get into bond formation a little bit later, and then we talk about kind of giving away electrons versus sharing electrons, because those are two different types of bonds. And we'll get to that in a little bit. But yeah, so these are the ones, like I said, 99% of the time, that's what you're going to talk about. Occasionally, you'll see sulfur, phosphorus, a little bit of nitrogen, and then some of the metals like manganese, iron, cobalt, magnesium. Every now and then, especially like at the very end of this biochemistry, you'll have a unit on the different minerals and stuff, and you'll see those way later on. But again, we're not going to be focusing so much on bond formation and stuff with those guys. That's just going to be their interactions within the body. So everything that's here in red, those are the big ones that we're going to see a lot of and that we want to focus on and really understand. So the forms that you're going to see these in, and this actually gets into the next question that's in it. So it's what is a cation? How are cations formed from an atom? And explain with an example. This is all just kind of one question they have together. So when we talk about certain atoms gaining or losing electrons, they form what are called ions. And specifically, well, the technical definition. So an ion specifically is an atom or molecule with a net electrical charge due to the loss or gain of one or more electron. So an ion is an atom with a charge because it has gained or lost electrons. Oop. Opened a new document. Here we go. So then we talk about these two. There's cations. I'm actually going to change this question. Cation versus anion. So a cation is going to be positive, net positive. This means that it is losing its electrons. An anion is net negative, means that it is gaining electrons. So those cations, the ones that we mostly talk about, we can see in that periodic table we circled, is hydrogen, it's a +1. Sodium is a +1. Potassium is a +1. Magnesium is a +2. And calcium is a +2. I mean, that's their charge. So we can correlate this directly back saying, okay, so we know how many electrons have they lost. If they have one more proton than they do electrons, that means they've lost 1. They've lost 1 electron and kept the same number of protons. Anions are they've lost the electrons, and that's going to be our oxygen at -2, our chlorine at -1, sulfur typically will go -2, fluorine -1, and so on and so forth. But we don't usually talk about fluorine. But oxygen and chlorine, those are the 2 main ones that we'll talk about. And again here, calcium, potassium, sodium, hydrogen, those are the big ones that we talk about. So how are the cations and anions formed from an atom? We already kind of gave these examples. Let me actually just put this up here. At the very end of this, I'll go ahead and send this whole document out, so that way everybody has a copy of it. And that way you don't have to, if you don't feel like copying every single thing that I'm saying down, you don't have to. And this way, like once I send this out, you can go back over it. And if there's anything that's still confusing, you can always ask me questions or add information, everything into here. So then how are these formed? We talked about here above that atoms are the happiest when their outermost shell is full. And so literally what happens is that because they have this they have their valence shell, and if they have an almost full valence shell, it's going to attract an additional electron. If they have an almost empty valence shell, it's more likely that electron, they're not going to be able to completely hold it, and it's going to go away. I don't want to get too deep into that because that starts getting into like energy levels of valence shells and everything. But this is about how deep we need to go with understanding what the main cations and anions are, that the cations are positive, the anions are negative. And if we think about if we know anything about electrical charges, what happens if you put a negative charge close to a positive charge?
Does it become neutral?
So it can become neutral, but why does it become neutral overall? Because if we think
Negative balances balance out.
They'll balance out. So they actually, negatives and positives, if you think about magnets, a magnet has a positive charge, a positive side and a negative side. If you hold the negative side close to the positive side, they stick together. If you hold the negative to the negative, they push apart. So just like that, these ions, if you take one that's positive and one that's negative and get them close enough together, they're more likely to actually stick together and combine and join together, forming a type of bond that we'll get into once we get down to this section of chemical bonding. Just a little bit of setup there. Let's see what these other questions are. We already kind of talked about these actually. How many electrons can completely fill the first orbit of an atom? We already talked about that. That's that first shell, 2 electrons. How many electrons can fill the second orbit of an atom? The second shell has 8 electrons. And which of the following 2 elements is the most electronegative? So this is where we haven't quite talked about this yet. Has anybody heard that word before, electronegativity?
Would it be oxygen because it's closer to the, like, I can't remember the 2 names, but like the ones closer to the upper right corner are the more electronegative?
Perfect, exactly. So as on the periodic table, let me actually pull up, I think I have a, there is a good, here we go, picture, just like you said right here. As we go more up and to the right here, we get more and more electronegative, excluding this last row because they have a full valence shell, so they don't need any more electrons. So all as we go up further and further up to the top right corner, it gets more and more electronegative. And
Sorry,
electronegativity.
can you explain the concept? Like, why does it get more electronegative?
Yeah. So what electronegative means is that it's a tendency to actually acquire those electrons and form the negative ions in chemical reactions. The reason why that actually happens has to do with how close, with the specific energy levels of like the pull that the protons have on the electrons, when they're in their valence shell. So, for example, let's look at oxygen, or actually we'll look at fluorine as to why it's technically the most electronegative out of all of them. So fluorine, let's see this. So we know that the protons themselves, so this is, let's say this red is the nucleus, and it's made up of protons. We'll pretend this is the same number as fluorine, and then neutrons, right? And with fluorine, we have the first valence shell has the 2, and then fluorine has the second valence shell. So it's kind of this philosophy that if there's a stronger negative charge and a positive charge, those two things, I don't know, are you able to see part of my camera as well?
What do you mean part of your camera?
Just like my actual face?
Yes,
My actual camera. Okay.
Yeah.
Sometimes I use my hands to talk, and I just want to make sure people can see that. So the stronger, like the more negative of a charge that you have, like the larger the negative charge, the closer it's going to pull towards the positive charge. The closer they're going to get to each other. And so the stronger they're actually going to, the atom is going to hold on to those electrons. So as we add electrons into fluorine, with each additional electron that we add, this valence shell actually would get slightly smaller because they would get slowly a little bit closer actually to the nucleus of the atom, which means that because it's closer, if another electron gets close and is just kind of floating out here, it's going to get pulled much more aggressively in order to finish that entire shell. That's like the super simplified version. If you want like a really deep answer as to why, that's a lot of like physics and much deeper into all the valence shells. But that's the simplified version for you guys.
This might be a dumb question. So we just have electrons just like floating around, waiting to be either bonded or shared or exchanged in a sense?
In a sense, yes. I mean, if you think about everything all around us is made up of atoms. Like even the air that we're breathing right now. The air that we're breathing is made up of nitrogen, of carbon dioxide, of oxygen, of a whole bunch of different atoms. And like when we breathe, we're literally breathing in different molecules and atoms in and out. So there really isn't, in the sense of like being on the Earth, unless you're out in like actual outer space. Here on the Earth, there is no quote unquote empty space. So things are constantly hitting each other, colliding into each other, kind of communicating in some way or another. So electrons are constantly kind of being passed along and given to other things. And also, this will make a little bit more sense when we get into the actual bonding. When we form bonds, especially ionic bonds, like when, for example, a hydrogen and an oxygen get close to each other, the hydrogen wants to get rid of its electron, so it's literally going to give its electron to the oxygen. So it's almost like passing it to it. So
is it the same within the body as like externally, like just breathing in air? Okay, perfect.
Yeah, because you think in the body, we've all heard the saying that we're all made up of 70% water.
Mhm.
So literally, you could kind of say that our body is literally just one big soup, and everything is mixing together, and it's very organized soup, but it's literally soup. Everything is kind of dissolved and floating around basically in water. It's kind of weird to think of the body like that, but that's
Yeah,
what it is.
it's a little nasty, but okay, it makes sense.
We're all just soup. Okay. Let me actually drop this picture into here. Electronegativity. Put that picture there. And also this definition. That way y'all have a beautiful little study guide. Okay.
So it's basically just the pull of the electrons, electronegtivity, like the strength of the pull of the electrons.
The pull of the atom, the nucleus of the atom on the electrons. So the atom itself, how strongly it pulls the electrons and holds on to them. Does that make sense?
Yes.
Okay, sweet. And that is that whole first chunk. And now we're going to go into chemical bonding. Personally, I think that this chemical bonding section might be the most important to understand for Biochem 1. We're going to talk a lot about bonds, different types of bonds, what the bonds do, and why specific bonds form or break. So, for example, so define ionic bonding with examples. So when we talk about ionic bonding, ionic is just the ions, which means atoms that have a charge. So this is going to be a positively charged ion, which is called what again?
Cation?
A cation is attracted to a negatively charged ion known as an anion. And the cation is going to give up those electrons to the anion. For example, one of the most common ionic bonds is H2O, water. So we saw that our hydrogen isn't super electronegative, and our oxygen is very electronegative. So our hydrogen wants to give away an electron, and the oxygen wants to take electrons. So pulling up a picture real quick. Come on. So let's get this picture bigger. This right here looks a little confusing. So this, the red is the oxygen, and these little pluses are the hydrogen. So we can see that when we're forming these bonds, the hydrogen want to give away their electron, so they're going to give their electron to the oxygen and become positive. So both of these now are positive, and the electron and the oxygen is now negative. So because they've given that electron to the oxygen that wants it, so the fully fill its last valence shell, now they're going to bond together because of that attraction between negative and positive. And that's literally what an ionic bond is you have
Sorry,
go ahead.
I have
Go
a
ahead.
question. So even though they are sharing electrons, they're not just like giving it away. Oxygen still becomes negative.
So with an ionic bond, they are giving it away. They're
Oh,
not
they are. Okay.
they're not sharing it. Yeah. The
Oh, okay,
oxygen
gotcha.
is literally ripping the electron away from the hydrogen, is stealing it from the hydrogen. The hydrogen willingly gives it to it, but because of that, then the oxygen becomes negative, the hydrogen becomes positive, and then they get bound together. When we say
Okay, okay.
bound together, they don't literally like the nucleus of them. The nucleus doesn't like squish together, but the bond is happening because the electrons are in the valence shell of the oxygen, and then the hydrogen has that outermost valence shell, and because it's positive, it gets attracted to that those negative electrons and gets stuck there.
So the oxygen doesn't like disintegrate or anything. It just attaches. It just bonds to the hydrogen. I mean, to the hydrogen.
Yeah, the hydrogen and the oxygen bind together because the oxygen is more negative. Each of the hydrogen is more positive, so they bind together because the positive and the negatives attract to each other. So I'm going to write this out, make sure. So the anion takes the electron and keeps it for itself. The cation gives its electron to the anion. And now because one is positive and the other negative, they get attracted to each other and form an ionic bond. Does ionic
hydrogen being -2 now? Since
go
ahead.
Yeah, so the oxygen would be -2, and then the water itself would bind, and each of those hydrogens give up electrons, so each of those would be +1. So then overall now we have a -2 and a +1 and a +1. So now overall the net charge becomes 0.
Okay, because it's the same on the inside and out.
Exactly.
Gotcha.
I want to see, does it ask about... One sec. I'm going to give a better example than the water, just because water, later on, we'll see water does some funky things. So let me give you a better example of an ionic bond.
Hey, there's another guy kind of joining the chat a little bit. I was going to ask on that, the water's ionic bonding, not covalent?
That's why I'm changing, because water has some ionic properties, but it does also technically covalent. It's kind of it's a funky one. That's why it's a bad example, and that's why I'm switching to a better example. For example, let's do instead sodium chloride, which is a much better example of an ionic bond. Like I said, it's been a little while since I've done all the general chemistry stuff, so I will make mistakes with this. Hopefully, if anybody everybody can help correct me, I would very much appreciate that.
No, thank you. I appreciate the discussion and the engagement. It's great.
Very much. Very grateful.
Yeah. And see, that's the great thing is we're all going to be wrong. I mean, look at me. I'm the tutor, and I'm still going to make mistakes. So it's fine if we make mistakes, if we get confused by things, because that's how we learn. This is a little bit of a better example. Sodium and chloride. So sodium wants to give an electron. Chlorine wants to take an electron. And so the chlorine is going to take the electron, and you have sodium and chlorine, and then those two are going to stick together. And another kind of way, or not a way, something that you can, a good thing to know about ionic bonds is that ionic bonds tend to break when they're put into water, also known as an aqueous solution. You'll see this kind of terminology used a lot, aqueous solution. That just means water. So if you put ionic bonds, if you put something that has an ionic bond, it's like NaCl. NaCl, if you don't know, is table salt. So if you put table salt in water, it will completely dissolve. Same thing if you think about like sugar. Sugar as well dissolves. Basically, if you put something that's kind of like minerally, like salt or something similar to it, and you put it in water and it dissolves, more than likely that is made up of some type of ionic bond.
Does that mean that ionic bond is like the weakest one?
Yeah, ionic bonds are pretty weak. There
Okay.
should be a chart. I think he has one in his. I made one at some point, but it's just.
Does aqueous always mean water, or is it just a liquid solution?
Aqueous itself is going to be technically water.
Okay.
You can technically use it for anything like wet, but more often than not, if it says aqueous solution, it's referring to water.
Okay.
It's just like it's one of those semantics thing of like what's technically quote unquote proper versus like what like the level that we're learning everything at. So yeah. Okay. So that is our ionic bonds where they're giving away the electrons. Then we have covalent bonds. So we're going to define covalent bonding. An example. So a covalent bond, this is where we have a chemical bond formed when electrons are shared between two atoms. So that's the big difference that you're going to see. And you will get asked this almost this exact type of question where it's going to ask like which of the following bonds shares electrons or which of the following takes electrons from the other. Something like that. You'll have some sort of question along those lines, either in a quiz form or in an exam form. So understand that the ionic bonds are going to take electrons, and the covalent bonds, the electrons are going to be shared between the two atoms. Let me actually open up. Let me see. Oh no, I know what I need to open up. Go. Biochem. 8 million things that I have on my desktop. Here it is. Okay. Okay, so specifically, the atoms, electrons are shared between the two atoms. Specifically, that they share the valence electrons between each other. Trying to think of a good example that we'll actually know. These will work. So within chemistry, that's not the right word that I want. Okay. I'll see if I can find that later. Okay. Covalent bond, one of the most common covalent bonds that we're going to see are something called, this is not going to be tested on, so I'm putting this for your information. Diatomic molecules is what they're called. This just means that two of the same atoms are bound together. Okay. So for example, like if we see, nope, wrong one. H2, something like this, where two hydrogens are bound together, or O2, something like that is bound together. All of those, that is a covalent type of bond known as diatomic molecules, and those are are fairly common. You might want to double check this as you go through the material and through the book and everything. But I believe Dr. Sarkar calls this element or elements when you have two of the same thing bound together like this. Which I'm not going to leave it here just because I'm not 100% confident in that. But I know it says it somewhere in the book. So as you're going through like the videos and stuff, just keep an eye out for that, because he has specific terminology that he'll use for stuff like this. I can't find the exact terminology right now, but I do recall him asking a question or two specific about that. It's just more kind of a definition type based thing. Okay. Any questions up to this point?
Well, I think that's pretty good.
Okay. Keep on going. So now we're going to talk about something that's polarity. So we have not bonds that are non-polar and bonds that are polar. Specifically, we're going to talk about, I think he only ever talks about them with covalent. Covalent, I can spell, covalent bond polarity. What polarity is, that one of the atoms is more electronegative in the bond, so it pulls the electrons closer to its nucleus, thus making that side of the molecule more negative. Let me actually switch this to polar there. So this would be something, an example, something like, let's go with NH is one example, which this is ammonia. Where if we go back up and we look at our electronegativity, nitrogen and hydrogen, nitrogen is more electronegative than hydrogen. So the electrons are going to get pulled more towards the nitrogen than they are the hydrogen. And so that the nitrogen side of the molecule is going to be more negative than the hydrogen side of the molecule, which just sort of kind of sets us up for extra stuff later on that we can see with bonding. Let me find there's a good picture that I know describes this or shows this really well. Also, I should say this, when I say molecule equals two different, two or more different atoms bound together makes a molecule. Just some definition type stuff. Something similar to this. Ammonia would look very similar to this. So this is just fluorine. This is fluorine and hydrogen. So because fluorine is much more electronegative, it's going to have a much more negative. This whole side of the molecule is going to be more negative, and this side is going to be more positive. And even, let me double check and actually confirm this, because okay. So according to the almighty Google, oxygen is a covalent bond. Sorry about the mistake earlier, guys. It's late. Okay, does this make sense about how there's sides of these molecules that are going to be more negative because the individual atoms are more electronegative? Does that all make sense? Does that make...
Yes. Are we going to be able to visually see that, or will we need to be able to like visually be able to see that that is happening, or just kind of be able to explain?
You'll want to understand that in order to answer specific questions about this, you'll want to understand the electronegativity. Understanding like those main molecules that we talked about, like the oxygen and chlorine and stuff, all through here. So like, if I remember, I think he has given a question or two in the past where it was like which of the following, like what side of the compound, what side of this molecule is going to be more electronegative or more is going to be more polar? Or I'll give you an example of, say, which of the following is a polar molecule? And so that's when you need to recognize, essentially, if you see something where you see anything that has like hydrogen or sodium or potassium, and then oxygen or fluorine or chlorine, which is a lot of different things, that most of what you will see, those are going to be polar. The ones that are typically non-polar are going to be these same ones, these diatomic molecules, where everything is split evenly. Where so the sharing of the electrons is perfectly balanced and even. So stuff like
is that going to come more when we need to start memorizing the periodic table?
You should have a decent idea. You don't need to memorize the whole thing because that's way too much. But I would have a decent understanding of those ones that we had circled earlier of these ones, specifically the ones in red. The ones in red, I would definitely understand. I'll add fluorine in there just because it's pretty. Yeah, these ones in red, I would understand. I would know. Let me actually put this down here. Let me put it up top. By this, I mean how electronegative are they compared to others, would basically meaning which is most electronegative. So like fluorine is the most electronegative, then it's oxygen, and nitrogen and chlorine are the same. And then these ones all over here are much, much less electronegative. That's what I mean by that. Honestly, if you know these two specific things, you'll be, or well, kind of three, you'll be pretty set when it comes to the periodic table. And then I guess along with this, remember the valence shells, the valence electrons, and how that is related to electronegativity and all that. What we talked about down below. Okay, hopefully that clears that up.
Do they not all form ions?
Most of them will, yeah. It's just like, it's more like eventually like you'll get into some like carbon, for example. Carbon and silicone, those are ones that kind of like do its own thing, but all of the other ones, yeah, pretty much will.
So for that first question, that's really all we need to know, that those two don't necessarily make them.
Yeah. That
Okay.
typically you won't see like a carbon 4+ or a carbon 4-. You won't see that. Carbon's
Okay.
just going to be at 4, and it's just going to bind to everything because it's carbon.
Got you.
Okay. In here, there's a lot of kind of repeat questions here. So what type of bond involves equal sharing of electrons? That is a non-polar covalent. What type of bond involves unequal sharing? That is a polar covalent. What type of...
Sorry, can you, I don't know if it's on there. Can you talk about the coordinate covalent bond? I don't know if I said it right.
What type? Coordinate covalent?
Yes. Because that was mentioned before too by in his presentation.
Yeah, you only talked about it like briefly when you went over it.
This is what the internet says. So a coordinate bond is a covalent bond, so a shared pair of electrons, in which both electrons come from the same atom. So let's look at an example of this. I don't know if there's a specific, it looks like here's a specific example with like nitrogen connecting to boron. Yeah. I don't think the only thing that he would probably ask about this would be a definition. I do not see him asking you to name any specific types of bonds or anything. So it would just want you to understand what a coordinate bond is. I don't see this coming up like in any specifics. So yeah, I would know definition of that, but you don't need to know anything beyond that.
Okay, I got you. Thank you.
This is kind of going back a little bit, but will we be able to like visually see if it's sharing the bond, or if they're like taking or giving it away, or will we know just by the name of, you know, what the what's in the equation? Does that make sense? Because they both, like from both pictures, it looked like, if you were to say if they both kind of look like they're sharing the electrons, like.
He's not going to give you pictures really, and any question that he does ask, that like which of the following is like covalent versus ionic, the kind of the trick is that with ionic bonds, like 99% of the time, where did our periodic table go? There it is. A grand majority of the time, if you're going to see any of the ionic bonds that he's going to be using, you're going to have some sort of like metal with it. So like sodium, potassium, magnesium, lithium, any of these, mostly sodium, potassium, mixed with something like chlorine or fluorine, oxygen. Those are going to be, even if you look up examples of ionic bonds, you can see it's like sodium chloride, sodium bromide, sodium fluoride, sodium iodide, potassium fluoride. So see, like you're almost always with ionic bonds, you're always going to have essentially look for like the sodium or the potassium, lithium, calcium, any of those, that group, those are going to form almost exclusively ionic bonds for what we're going to look at. Yeah.
Can you like pin that or add that to like the chat anyway?
I'll just add it into this document so that way you guys can see it later.
Perfect. Thank you.
And this is what's really cool about this is why I wanted more people here, because we can add these different things to it like this, and it becomes a much more comprehensive study sheet. Okay. We're just going to answer this question. So what kind of bond is present in an ethane molecule? CH3 and CH3. So it's two CH3s all together. So if we literally draw this, see, you'll see this a lot in chemistry, and you don't ever really talk about it. If you just have a line coming off of a carbon, it is assumed that there is a hydrogen there. Okay, so it won't always be written, but it's assumed if it's just a blank line and nothing connecting to it, it's assumed that there's a hydrogen bonding there. So you'll see it like this. So through all of this, if we were to think about electronegativity, the amount that gets pulled in each and every single direction are all going to be equal to each other. So this is pulling electrons this way. This is pulling electrons this way, the same strength. So all of these forces get canceled out, and this is a non-polar molecule. So something like ethane is a non-polar. If we were to identify the type of bond between two carbons, for example, what would we call that bond?
The elements.
So think about I guess, so carbon to carbon, first of all, is it going to be ionic or is it going to be covalent?
Ionic.
So I think is one of the carbons going to be giving up electrons, or are they going to be sharing the electrons?
It's going to be covalent, right?
Yep. So they're going to be sharing electrons, and that's going to be a covalent bond. So then we look at it, is it going to be polar or is it going to be non-polar?
It's going to be non-polar because they share them equally, correct?
Exactly, because the electronegativity between both of them is the exact same. So it's both going to be pulling the same amount. So this is a non-polar covalent bond.
Is that because there's no like a +1 or a +2? It's just C and C?
Exactly. Yeah.
Perfect. Okay.
And then CH, carbon, hydrogen. First of all, is this going to be covalent or is it going to be ionic?
I think ionic.
So we think carbon. Does carbon typically, does carbon give off or take on more electrons? What does it like to do?
I would have to see the periodic table.
Carbon just chills out.
Oh, yeah.
Does not form an ion. So if carbon does not going to form an ion, can we have an ionic bond?
No.
For the purpose of this course, there's no ionic bonds with carbon. In the real world, there's like lots of random little nuanced stuff, but we're not worrying about the real world. We're worrying about Biochem 1 and getting through try 1 of Parker. So if we have a carbon and a hydrogen, and they're bound together. Looking at our electronegativity chart right here, hydrogen is a 2.1, carbon is hidden right there, but it's a 2.5. So is this going to be polar or nonpolar? So CH is a covalent bond. And because carbon is more electronegative, it is polar.
Okay. Yeah.
So it is CH is a polar covalent bond.
So do we always want to distinguish whether it's ionic or covalent first before going to polar and nonpolar?
Yes,
Okay.
definitely. So if we talk about that, ionic bonds themselves, can they be nonpolar?
No, I don't think so.
Exactly. The ionic bonds, because they're ionic bonds, you have a negative side and a positive side. And like the negative side is taking away the electron. They're always going to be technically polar. We typically don't label them as polar because if you give them the name ionic, it's just assumed that they are polar. Good input. So now we move into something called hydrogen bonds. So I want you to do something really, really clearly. So hydrogen bonds, let me actually put this on the study guide. So that was covalent ionic bonds. We have covalent bonds. And now we're going to be talking about hydrogen bonds. The first thing I want to say, hydrogen bonds are not covalent bonds. Okay, make sure this is very clear. They are not covalent bonds. There's their own category of bonds. Okay. Make sure get a less chemistry. Okay. This is a good definition. So a hydrogen bond is an attraction between two atoms that already participate in other chemical bonds. A really good way to think about hydrogen bonds, kind of what they do. Has anybody ever like filled up a cup all the way to the very top and just kept adding drops of water? And you almost get like this dome of water up over the top of the cup?
Yes.
So if you haven't tried that, I recommend you try it. It's really, really interesting. What you're actually observing there is hydrogen bonds. You have a bunch of different molecules, so H2O molecules, that already are bound, and oxygen and hydrogen are already bound. And then, but the because they have that polarity to them, they are able to have it's like a secondary bond with, let me put a picture. They're able to form like a secondary bond with the other H2Os around them. So if we look, where's my, here, nope, go away.
By secondary, you mean they're just continuously like bonding with everything, with each other?
Exactly. Yeah, exactly.
Okay.
So if we look at these, we looked at oxygen or at an H2O molecule before, and we said that H2O is not only a covalent bond, but it is also a polar bond, right? So it is a polar covalent bond. So we have all this negative up here. This whole part is more negative, and this part is more positive. And then we think, well, positives and negatives attract each other. So we have here, each of these oxygens are more negative, and the hydrogen part of this molecule is more positive. So then the positive forms this hydrogen bond with the negative part of the other oxygen molecule close by it. And that's what a hydrogen bond is. And it's called a hydrogen bond because, at least what we'll talk about, it's essentially exclusively when a hydrogen that is in some sort of polar molecule is then going to bind to another polar molecule. And this doesn't just happen with water. Later on, we'll talk about like proteins and stuff and how they form and how they get shaped, along with like the different we have amino acids. The amino acids get put together in a certain way to form proteins, and the hydrogen bonds help fold and shape our different proteins, which I think within the first couple of weeks in Cells and Tissues, you guys talk about that. And then you talk about it again later on in biochemistry. So there's a decent amount of overlap between each of your classes that you'll start to see. Any questions about hydrogen bonds? Okay. Okay. That kind of answers a couple of these questions. Exactly what we were just talking about. We already answered those. So the chemical bond formed between two atoms of hydrogen in a gaseous hydrogen molecule is an example of what kind of bond? So we have a hydrogen connecting a hydrogen. First of all, is this going to be ionic or is it going to be covalent?
I'd say ionic.
So let's break that down. Why do you say ionic?
I don't know, because it's the same, two of the same atoms, basically.
So they're two of the same, right? When we have an ionic bond, we need one atom that's going to give electrons and another atom that wants to take electrons.
Oh, okay, I think,
right?
yes, it's a covalent. Yeah, I think I mixed them up.
Good. I just want to make sure that that's clear.
I got you.
It's great. That's why when we learn more from our mistakes than we do from being right. So again, so with those ionic bonds, we want to look and see, okay, is there something here that wants to take electrons, and is there something that wants to give electrons? And that's kind of a way that you can tell whether or not you have an ionic or covalent. Any time that you have two of the same exact atom binding to each other, it's going to be a covalent bond. So this is covalent. And because it's both the same, they're going to have the same level of electronegativity. So it is a non-polar covalent bond. Then what kind of bonds hold the molecules of water together? Again, this is hydrogen bonds. We just talked all about those. Identify the hydrogen bond and a covalent bond in the molecules illustrated below. We can look, this bond right here, is that hydrogen or covalent?
Hydrogen.
So if we look, the definition of a hydrogen bond, right? Where'd it go? Definition of hydrogen bond is a hydrogen bond is an attraction between two atoms that already participate in other chemical bonds. So we have one molecule here and a separate molecule here. So this is the original bond that hydrogen is forming with oxygen, the original bond. So these two here are our covalent bonds.
Mhm.
Same with these two down here. Are those original bonds are covalent bonds. And then the bond in between the two of them is now our hydrogen bond. Okay, and then we say this part says show the ionic charges present in oxygen and hydrogen atoms. What this means, ionic charges, is referring to polarity. What parts, there's polarity, what parts are positive and what parts are negative. So the oxygen is more negative, hydrogen are both more positive, oxygen more negative, hydrogen more positive. Positive and negative like to connect, and that's how we get our hydrogen bonds.
Would he ask us to do this on like a test question, like when we're
No,
drawing?
no. He won't ask you to do anything like this. It's just more understanding the concept. And to be frank, a good bit of all of this material isn't going to specifically be asked, like all of this review stuff, this isn't going to be asked on the exam. Like this specific type of things. A handful of things, yes. But a good majority of it is setup material, where a lot of the stuff that's in here we need to really understand to be able to understand the future material and to understand the future questions. So that's kind of why we're doing this, because in all honesty, if we get these basics down, understanding the different types of bonds and how they form and why they form, then when we start talking about all of a sudden like the creation of proteins and how the proteins form and everything, he's going to jump over that whole chunk, just assuming that you understand it, and ask questions on like that second level with like the formation of those things.
Okay.
So this next question, does a water molecule have polarity? Show the polarity. That's exactly what we have right here. So it is a polar covalent bond. Write down the chemical equation showing the dissociation or ionization of the water molecule. So here we go. Some new words for us. Come on. So dissociation, we talk about dissociation, we're talking about the breaking up of a compound into simpler parts that are usually capable of recombining under other conditions. Let me actually put this. Dissociation or ionization of water molecule. I can spell. This is why I don't handwrite stuff, because if I did, I'd still misspell everything.
Same, I started typing everything.
Okay, so dissociation in chemistry is the breaking up of a compound into simpler parts that are usually able to come back together under other conditions. I like if you have a definition that uses big words, make it as simple as you possibly can. That way when you come back, you don't have to be thinking about it as you're reading those definitions. So here you go. This is ionization. Ionization is any process by which electrically neutral atoms or molecules are converted to electrically charged atoms or molecules, called ions, through gaining or losing electrons. And to be completely honest, I don't know why it's talking about ionization of water molecules or dissociation of water molecules, because really we won't talk about that a lot. So I'm not going to spend a lot of time right now going over it, just because it's not really pertinent to a lot of the other information that we need.
Hey, just a question. Are we going to be doing this? Can we do this like every week with you?
We can try. It just depends right now my schedule, because I just started clinic, and my wife works nights So it's a little bit hard for me to give a specific one specific day each week.
Mm-hmm.
But if it's something that we really want to do, we can do it on like a week by week basis, and
Yes,
figure out
please.
a specific day each week to do this or something
That would
like
be
this.
perfect.
Yeah. The other part, that's one of the reasons why, if you have not seen, I have posted a couple times, but one of the reasons why I made the YouTube channel was to kind of get away from the meetings where I would just go over the material in the book like that. So my ideal would be that, because once we get through all of this material, there's not really a whole lot that I can do as far as like leading. It would be more like I would need a group of people to come with specific questions, and we would
Mhm.
answer those specific questions and work through those specific topics at that time. So that would be, I don't want to do like going through the book or just like me teaching a specific chapter when I've already done that in those YouTube videos and stuff that I put together.
Mhm.
Okay, so you want to do like kind of review kind of deal.
Exactly. That's what I would much rather do.
Okay.
And is in the past, I've scheduled sessions and stuff like that, and you'll realize that when, again, we can play this by ear, where often there can be one or two people that typically will show up consistently, and then it slowly dwindles and decreases as people get more and more busy. So, well, we can start to do this once a week and kind of play it by ear and see how many people are showing up and what we would like to do each week. Sound good?
Sounds good. Yeah, sounds
Perfect.
good. Thank you.
Okay. This is one he has. If you've not already heard him say this, he says it about 100 times. He says, like dissolves like. Have you heard him say that already?
No.
Really? Have to ask him about that, because when we talk about this, let me write down the question. What type of solutes can be dissolved or are insoluble in water? First things first, solutes versus solvent. I always got these mixed up. Solutes are the stuff that you are putting into the liquid. Solvent is the liquid you are putting stuff into. Solutes are the stuff, solvent is the liquid. Okay. And there's a rule that we follow that like dissolves like, which means things that are similar to each other are going to dissolve each other. For example, if we talk about the classic water and oil, they do not mix. And this is actually because of their chemical composition. Water is polar, oil is nonpolar. So if we look at it, so if you try and mix water and oil, it's just not going to go together. But if you were to mix something like vinegar and water, both are polar compounds and will dissolve. I'd say combine into one another. Does this concept make sense?
Yes.
Okay. So to put it in more descriptive terms, polar molecules need to, let's say, polar solutes need to be put into a polar solvent in order to mix. non-polar solutes need to be put into non-polar solvent in order to mix. That's the big main idea with that. And so the same thing, if you get a question like, will this specific compound dissolve in whatever, you need to look at both of them and say, well, is this solute? Is this polar? Is this ionic? Is it polar or is it nonpolar? And then you look at the solvent, the liquid. Is it polar? Is it nonpolar? Or what is it? And then if they match, they'll dissolve into each other. If not, they won't. Okay, then we get into types of solutions. I'll actually add this here. Solute plus solvent equals a solution. So once you add the solute into the solvent, it becomes a solution. A lot of this vocabulary type stuff, like these, I really, really, really recommend that you learn these well, because you will start to get questions literally as simple as which of the following is the solute in this whatever, in this situation, which of the following is the solvent in this situation. And a lot of people mix up what a solute and a solvent is. And those are some of the freest points that you can get. And if you miss easy points, it's a lot harder to make up for missing the harder points. Okay, different types of solutions. We have isotonic, hypertonic, and hypotonic. Another piece, another something that I really recommend is starting to learn the prefixes and the suffixes of the words. For example, iso means the same. Hyper means high or excess. Hypo is low or what's a better word for insufficient, maybe? Yeah, I would say it's lower. So when you start to, and whenever you see these words, you'll see them a lot later on, like in physiology next trimester. You'll see a lot of hyper, hypos, isos, all that sort of stuff. Understanding the prefixes are going to make sure that you are able to, whenever you see new words, understand them a little bit better than you otherwise would. Okay. The way that he wants us to learn these, specifically, we usually talk about them within a cell. So you'll see some sort of image like this. Maybe if it... So I want to come, here we go, there. We'll see something like this. Hypertonic, isotonic, and hypotonic. Here's another picture. This one's probably actually better. Okay, we'll start with the isotonic solution. So within an isotonic solution, it means that there is the same concentration of stuff, those solvents, solutes, same concentration of stuff mixed into this solvent outside of a cell as there is inside of a cell. So that means the liquid that's inside of the cell has the same concentration of solutes mixed into it as the outside of the cell. So that means water is not going to move and the cell stays the same size. Okay. a hypertonic solution, this one here, the first one, the cell is going to shrink. And that is because the concentration of the solutes mixed into the solvent outside of the cell is much higher than inside of the cell. So water flows out of the cell and the cell shrinks. I promise you you're going to have at least 1 or 2 questions literally like exactly like this, if not just in this class, but you'll also get asked this next trimester in physiology as well as in microbiology. And I think you also will have this type of question in cells and tissues. Because this is something that for some reason a lot of people get really mixed up on. Okay, we talk about hypotonic solution. The way that I remember hypo, hippo, where the concentration of those solutes mixed into the solvent inside of a cell is much higher than outside of the cell. So water flows into the cell and the cell expands. It's big like a hippo. Yeah, I cannot tell you how many times people get points off because of these questions. Okay, these should be free. Give me the points questions. Just make sure you know the definitions. And that is what is hypertonic, isotonic, what happens if you put a cell in each of those. This question, why sometimes do we need to put a living cell in an isotonic solution during certain experimentation? This isn't really relevant to like the rest of the course, but it's literally just because we need to keep everything the same. We don't want the cell expanding or shrinking due to just the solution that we put it into. We want it to see how it responds or reacts to whatever the experiment is that we're doing. So don't worry about this question, really. It's kind of just an extra whatever, just a thinker question. Okay. Acids, bases, and buffers. How's everybody doing? We've kind of been, I know we've been grinding through for a little while.
I'm good so far.
Okay. You pull up. Have you guys covered the acids and base chapters already?
Yes.
Yes, okay. Okay. We'll start with acid. So first, define an acid. So an acid, in chemistry, there's technically a couple different definitions for acid, but the definition that we are going to use for biochemistry is a compound that releases protons, also known as hydrogen, when put into a solution, is a proton donor. This is the definition you need to remember. Again, you will get asked questions that is just a simple definition like this, or it'll give example like which of the following would be an acid. and you need to pick whichever one has additional protons, and that would be more likely to give away those protons. Okay. Let me see if it includes some other stuff down here. Okay. I'll take a minute to talk about this here. We split acids into two different groups of weak versus strong acids. Okay. So weak acids, these are going to be acids that do not completely dissolve, also known as dissociate, when put into a solution. So in this case, the acid is acting as the acid is going to be our, I don't want to put that there yet. We'll get there a little bit later. So when we put the acid into a solution, a weak acid is not going to completely dissolve or dissociate. Okay. This means that it does not donate all of its hydrogen ions / protons, SH plus, whatever you want to call it, to the solution. Then we have strong acids. These are going to be acids that do completely dissolve or dissociate when put into a solution. So it donates all of its hydrogen ions to the solution. It's important to realize like what kind of acid is, because when we talk about these different acids, especially weak acids we're going to be using for something called a buffer system, which we'll get into in a little bit. But it's thanks to these weak acids that, for example, carbon dioxide that gets produced in our muscles, that we're actually able to take that carbon dioxide out of the muscles, put it into the blood, travel it through the blood all the way to the lungs, and then release it from the blood into the lungs for us to breathe out. Without these specific acid in the buffer systems, our body would not be able to function properly.
Do we need to know the weak acids and the strong acids, like a list of them?
I think he gives a couple of examples in the book. If he gives a couple of examples, he might ask a question on those. Like I know strong acids, like the most common ones, are like hydrochloric acid and sulfuric acid. I think those are like the only two that he lists in the book. And then
is there a way to like recognize them, or is it just like you learn and you remember?
Learn and remember. As far as I know, I'm sure that there is. But that would probably be down a rabbit hole of, well, let's find out. Let's see what Google says. Maybe there is an easy way to recognize them, and I've just been doing it the hard way my whole life.
That would be nice.
Huh. Chlorine, bromine, and iodine. And probably sulfur as well. Let's see.
Okay, so it does have to have hydrogen and then whatever.
I guess I would say in general, yeah, an acid is going to have hydrogen. And if it's an acid, there's going to be hydrogen present because in order to be a proton donor, it has to have protons to donate.
Yeah, that makes sense.
So I guess specifically, some like the strong acids are going to have chlorine, bromine, and iodine. And then there are other acids as well, but I don't think. I mean, again, this is a rabbit hole we could go down. If you want to spend a little bit of time doing that, looks like there's a couple of videos and stuff. I always recommend if you want to go down a little rabbit hole to understand something better, go for it. If you have a little bit of time to do it, the only thing that can happen is that you learn something. Just when you do go down those little rabbit holes, make sure that you don't go too far down and start to freak out thinking that you need to know all of this
confused.
stuff. Yeah. So my best recommendation is stick to what is in the slides and what is in the book. So like if it lists specific acids in the book to know about weak and strong acids, which I'm pretty sure that it does at some point, I would recommend learning those specific acids because that's going to be kind of your best bet. Majority of your professors, like especially Dr. Sarkar, they're not trying to trick you. They're trying to test you with the information that they've given you. But at one place or another, they have given you the information that they are asking. It's just whether or not we have found it, studied it, and are able to recall it when we get to the exam. Okay. Now we're talking about, so that was acids. So we define now a base. So a base is a compound that accepts protons or lowers the hydrogen levels of a solution or releases hydroxyl ions, or these OH ions. So the base definition is a little bit longer in that it can either accept the proton, it can lower the hydrogen levels, which actually I would say even cut this part out. Compound that lowers the hydrogen levels of a solution by accepting protons or releasing hydroxyl ions. That's a better definition. Reworked it a little bit. Okay, and just like we had, so this is going to be, it is a proton acceptor or gives OH. And just like the acids, we have a weak bases and we have strong bases. And it's the exact same definition where the weak bases are going to not dissociate completely, so they do not completely dissolve, and the strong bases are going to completely dissolve. If you want, you can go back later and throw in the definitions there, but it's identical to weak versus strong, and same exact idea as with the acids. Okay. Now we get to what is called a buffer. So a buffer is composed of a weak acid and something called its conjugate base. This is usually where we tend to lose people. So first off here, this is where we really want to pay attention. When we talk about a conjugate base, kind of what that means. So we think about the whole process. Let me find an example. I just want to focus on this top part right here at the top. Okay. So HNO2, this is an example of a weak acid. And then we're putting it into water, which is a base. So it's going to not fully dissolve, but it's going to partially dissolve. And as a result, you get what's called the conjugate acid and the conjugate base. The conjugate base is just the weak acid with the hydrogen removed. Okay. Any confusion with that? I'll take the silence as a no. So the weak acid without the hydrogen, so the hydrogen has been removed once it's put into the liquid. That is its conjugate base. So a buffer system is a weak acid and the conjugate base kind of working together. And this double-sided arrow here means that this flows back and forth. So we constantly have acid combining with the weak acid, constantly binding with water to form free hydrogen ions and its conjugate base. And then we also constantly have conjugate base combining with hydrogen ions, turning back into the acid and water. It just depends on which direction is happening faster. So if you put a weak acid into water, it's going to be going from the acid to the conjugate base, typically faster than the conjugate base is turning back into the acid, until it eventually reaches an equilibrium point where then the rate is the same going back and forth. Okay.
Is the base always H2O?
For our purposes, yeah, we're pretty much always going to use water.
Okay.
Like you can technically use other things, but for our level of chemistry that we want to know, we're going to be using H2O. So this whole thing right here, this is what a buffer is. It's just that weak acid and its conjugate base, and that's how it goes. It travels back and forth. Is a question?
I don't know. Maybe it's stupid, but it looks like we're losing the water, but I know we're actually not. Oh, it's not.
Yeah, so we're not losing the water. So actually we're not losing the water. I guess you could say it's just because when you add it into the water, this is the way that they're going to write the equation. But you could technically also write it just like this. So
I mean,
weak acid
it gets dissolved,
goes
right?
to
in the water, I guess.
Yeah. It dissolves, it mixes with the water.
So okay, that's why it looks like we're like don't have water anymore.
Yeah. It's just
Okay,
mixed in
makes
with
sense.
water. You can also write it just like this. And technically this would also be like an arrow sign going both ways. So the weak acid turns into the free hydrogen and conjugate base, and then the conjugate base will combine with more hydrogen and go back to the weak acid and back and forth, just at different rates. Until eventually it reaches an equilibrium point, which means that at equilibrium, it means the same amount of acid is going one way as the conjugate base is going the other way. So it stays constant at that point, which means that it's dissolved as much as it's going to dissolve, and as much hydrogen that is going to be released has been released. That's about as deep into buffer systems as we really go in this course.
Is it the same for the conjugate base? I mean acid, or?
Yeah, well, it's what do you mean?
Because right now you only have the base up there, so is it the same for the acid?
I'm not sure exactly what you're asking. Are you talking about conjugate base? Or are you talking
Yeah,
about
it's we
conjugate
have
acid?
conjugate base and conjugate acid. So is it
So-
the same?
So
Or?
if you put a weak acid in, you're going to get conjugate acid, hydrogen, and conjugate base here. The conjugate acid is just the hydrogen. And to be honest, we typically don't even call it conjugate acid. I would just ignore that for this class. And just focus on it's the weak acid and its conjugate base forms a buffer system.
So
Okay.
the equation below is an example of what a buffer system is, correct?
Yes, this is what a buffer system looks like, where you have some form of weak acid getting put into water, and that weak acid dissolves into hydrogen and a conjugate base.
And you know it's a weak acid just by like memorizing the HNO2.
Yeah, just by knowing which the weak acids are. That's why, like, the way that he's going to ask you guys these sort of questions, like, he might ask you based off like the specific examples that he has in the book, but like he's not expecting you guys to be master chemists. Like, he doesn't want you to do, you are not going to have to do all of like the equations and stuff, and he's not going to be mean with this sort of stuff. It's more understanding the concept about when you put a weak acid into water, what happens. You're going to get hydrogen released, and you're going to get the conjugate base then is now in the solution. And then we get into what's called titration, where then you add more of the conjugate base into the solution. And if you increase the amount of conjugate base into the solution, it's going to drive this reaction and push it more towards this direction. So if you add more conjugate base, it's more likely to combine with the hydrogen and it's going to push it this way, which means that there's less free floating hydrogen in the solution.
Will it go back to an equilibrium, or will it stay at a higher?
Eventually, if you stop adding conjugate base or you stop adding acid, eventually it will reach an equilibrium point. And that's what a lot of these experiments and stuff are based on. Is like adding different chemicals, kind of back and forth, trying to find a very specific balance point.
Okay.
So within the body, this is something that this was more what you'll get in physiology next trimester. The entire body is all about homeostasis, which means keeping a balance within the body of everything. We're about to talk about this next. The body has a very specific pH. pH is essentially a calculation used to figure out how many ions of hydrogen there are. And we measure that on a scale of 1 to 14. The body has to be between 7.35 and 7.45 pH to survive. So we have this very, very small window in order to be alive. And so because of that, we have to monitor and maintain our hydrogen ion levels very, very carefully, which is why we have buffer systems. For example, we have the bicarbonate buffer system. We have a hemoglobin buffer system, and we have a phosphate buffer system. You'll talk a lot more about these. You don't need to know the specifics of these right now. You'll talk more about these in physiology next trimester. But the idea behind all of these is like bicarbonate buffer system, for example. This is talking about the carbon dioxide that our muscles give off when we exercise and when we use them. When carbon dioxide, let me actually pull up the. So CO2 plus H2O becomes H2CO3. If we look at this, we can actually even kind of swap these things around. And rewrite it. This is still the exact same thing. But this right here, this H2CO3, that's a weak acid. CO2 is going to be its conjugate base. And release these numbers don't quite exactly add up. Like this equation is a little bit more complicated. Like you'd have to you get other stuff in here, but just for demonstration purposes. But this is literally a weak acid and its conjugate base and free hydrogen. So as our body produces more CO2, and we have an increase in the amount of CO2 here, it's going to force this reaction towards forming this bicarbonate. And the bicarbonate then can travel in the blood. And when it gets eventually back to the lungs, it can switch and back in CO2. And this is helping maintain our bodies, like locking up some of this hydrogen to keep our pH in balance. So again, like I just said, you do not need to know this specific system. This is above your pay grade right now. But this is something like this is why we have these buffer systems and how they work in physiology. This is just like a glimpse into the future of what you'll see later on down the road, just so that you have a little bit of context to what it is. Okay. Cool. Okay. So that's our buffer systems, what the purpose of our buffer systems are. Say buffer systems are meant to maintain pH homeostasis. Okay. Hopefully I didn't lose anybody there. The parts that you need to know, you need to understand what a buffer system is, that it's the weak acid and its conjugate base, what a conjugate base is, and this general kind of formula. And now we're going to get into pH, which is what the buffer system actually deals with. So literally pH is the measurement of how much hydrogen or how many hydrogen ions there are in a solution. If we think of our body like that soup, our whole entire body is a solution. It's water with a bunch of stuff mixed into it. And so we're checking to see exactly how many hydrogen ions there are and making sure that there's not too many, or there's not too many, there's not too little. Let me pull up. There's another equation that he wants you to know. Yeah, this equation. This is the equation that is used. This is more math stuff. You don't need to know how to do the equation. You just need to understand that this is what the equation looks like. That pH equals the negative log. These little brackets, anytime you see brackets, that means concentration. So brackets equals concentration of something, which means the amount of stuff of that specific stuff mixed into a liquid. Okay. That's the equation for pH. Again, like I said, you don't need to know how to use it. You just need to know that that's the equation and be able to recognize it if he asks a test question on like which of the following is the pH equation. Okay. That's as far as you need to go. When we talk about the range, easiest done through a picture. This is what it looks like. Acidic equals more hydrogen ions are present. Alkaline equals basic equals less hydrogen ions are present. Okay, and 7 is neutral. Remember, the human body, we have to be between 7.35 and 7.45 to survive. Very specific range, which is pretty crazy. Okay, any questions specifically about the pH, about pH itself, what it is, or how we rate it?
I do have a question. In your video, you mentioned that if we go out of our pH range, it means death. What do you mean? Like, what is so bad if our pH is out of that range?
Yeah, we'll talk a lot about this. You'll talk more about this when we get into proteins. But proteins within the body, which literally do everything for us, they have a very specific pH range in which they function. So certain things can disrupt the function of our proteins, stuff like temperatures. So for example, if our body gets above 104, 105 degrees for a certain period of time, our proteins will literally start to break down and we get death of tissue. So just like if our pH gets too high or too low, our proteins will literally start to unravel and unwind and no longer function. And if they're not functioning, that means tissue and cell death.
Okay, got you.
Yeah. Not fun stuff. Okay. Next part. This is one thing that everybody hates. The Henderson-Hasselbalch equation. Hasselbalch, I don't know how it's supposed to be spelled. Doesn't matter. Actually, I do want to make sure that this is clear up here real quick. Basic. So this is literally, it's kind of backwards what people think. So high pH means low hydrogen. Low pH equals high hydrogen. So they're reverse of each other. You'll get asked a handful of questions like this about your pH is whatever number. Is this acidic or is this basic? Or like you add this specific thing. And if it looks anything like this, if it has a hydrogen on it, just with hydrogen, understand that that's going to make things. So if you add an acid into a solution, it releases hydrogen and decreases this number. If you add a base or a conjugate base into a solution, it's going to make it more basic. Where are my Henderson-Hasselbalch? Okay, so this is our Henderson-Hasselbalch equation right here. do this. Here we go. So what I do every single time, you'll want to start doing this now. If you can start doing this now, you'll be in a much better shape throughout the whole trimester. Every single time that there's an equation like this, I want you to break down each of the variables and write out what they actually are. So pH is the concentration of hydrogen ions. pKa, we have the A minus and the HA. So pKa is going to be a constant. This is not something that this is something that, like, if you were to be doing these equations, would have to be given to you. The pKa, this is a constant based on the specific acid you are using that tells us how weak or strong the acid is. So this is something that is specific to each individual acid. And if you were to need to actually do any equations or anything like this, they would have to specifically give you the pKa value in order to solve an equation like this. Or they'd have to give you the pH and everything else, and you'd rearrange to solve for the pKa. Okay. So that's all it is. It's just a constant based on the specific acid saying how strong or weak it is. And that's figured out in a lab by doing experiments and measuring all, like, when they'll put a certain amount of acid into water and then measure exactly how much of the acid broke down. Okay. Okay. The other parts of this, I want to make sure that I have them correct. The concentration HA, this is going to be, remember the brackets mean concentration, so this is concentration of the weak, or of the acid, and this is the concentration of the conjugate base. And all of these together can be used to create this equation, and with this equation, they can figure out, you're able to figure out the pH based on these different values. And then he wants you to specifically know this one fact: at equal concentrations of conjugate base and acid, the pH is equal to pKa. This is literally right here how he's going to ask that question. He'll want you to have just understand this concept. He might ask it with a lot of words. That's the biggest complaint people get with Dr. Sarkar's class, is that sometimes he'll use a lot of words in his questions. And so you need to read all of the words in order to understand, understand the whole question. This is the big reason why throughout this whole thing I've been listing, like, vocab words. Because if you at any point get confused by vocab, like if it says solute versus solvent versus aqueous solution, molecule versus compound, like all of those sort of things, that is where sometimes stuff gets lost. And that's where, if it takes you a long time to read and understand the question, you don't have as much time to answer it. And that's where people tend to have struggle with this class, is just understanding what the questions are asking to be able to, and what the answers are saying in order to answer them appropriately. So that's why know your definitions and your vocab.
If I ask a question real quick?
Yeah.
But actually more so just on advice. I didn't prepare myself that well, and I got the book that, I don't have Saker's book. Should I get it?
Yes. If you want, depending on what you want, if you have I can share the PDF version with anybody who wants it.
That's right. I'm having a hard time getting on that Teams where like everybody had those books.
Yeah, in the Biochem 1 group chat. Let me pull it up quick. My 8,000 group chats that I'm in.
Thank you for this. For whatever reason, I'm on like the old online classes. I'm on like the organic chemistry teams or something, and I'm like just haven't figured out.
Yeah, if you go up to the pinned messages, it should be pinned here somewhere. Let it load. I don't know why it's not loading. Might just be because it's further back. I put in here, right here. There's a Google Doc right here. Oh, actually, no, it's not that one. I put in a link to all of the Try One books that I had. It's here somewhere.
So I can go through and find that. Thank you so much. That's great.
Yeah, I can reshare that later on if you need me to. Just shoot me a message and I can get that to you. Yeah.
Okay, awesome. Will.
Okay. Another thing, I'll plug the YouTube channel here. Because even if you don't have the book, I know for me personally, I'm not very good at reading, like sitting down to just read. I kind of hate it. This is a YouTube channel that I've started this last trimester. And I actually have a specific biochemistry playlist. Oh, good. If I go to, I want to see the whole playlist. There we go. So this literally starts from chapter 1, and I go through every single part of the entire textbook, as well as adding additional bits and pieces, trying to connect it to other classes, previous tutoring practices and stuff. So yeah, this is the entire, but I did a final exam review last trimester, which is like 3 hours long, going through the entire, like all of the entire class. So yeah, if you didn't know about it here, this is all of that.
I'll definitely be using that. I think I bookmarked that. So
by chance, do you know if there's anyone who made something similar for biologies of cells and tissues?
Nobody has at this point. My dream goal would be essentially to create something, to continue to create these types of videos for almost every single class at Parker that people struggle with. Cells and, like biology of cells and tissues is another one that people tend to struggle with. But unfortunately, I'm one person and I don't have all the time to do that. So eventually I will try to get that. But for right now, as far as I know of, there's not something like that available.
Do you think you'll have time to have like sessions like this, but for biologies for cells and tissues?
Probably not, unfortunately.
Okay.
Just like right now I am actually also tutoring biochemistry 2 as well as physiology 1. Those are another 2 courses that people really tend to struggle with. And I'm recording videos for both of those courses right now as well. So it's quite an undertaking, to say the least. So,
No,
and
I appreciate you very much for whatever you can offer.
I'm only allowed to work so many hours a week. Otherwise, like if I hit a maximum number of hours during a trimester, they literally come and tell me, hey, you can't work anymore. So it's I'm trying to get as much as I can done through all of the different obstacles. But yeah, it's all part of the game. Okay. Jumping back in though, so the Henderson-Hasselbalch equation, this is the whole equation. Make sure you understand what each of these things represent, because he could ask questions something like, if you increase the amount of bracket HA bracket, what would occur? What would happen to the pH? kind of, he would ask it in more words, but that's kind of a question that he would sort of ask. And so if we literally look at this, I would recommend get a calculator out, plug this equation in, make up a number for pKa, and play with it a little bit. See if we increase the value of the conjugate base, what happens to the pH? If we increase the value of this, what happens to the pH? And you should be able to identify that without actually having to do the calculation if you understand what it's saying. So for example, we know if we add more conjugate base, if we increase the concentration of the conjugate base, just like we talked about up here, we increase the concentration of that conjugate base, it's going to absorb more of the hydrogen because it's going to drive the equation back this way. And so we're going to have less free hydrogen, so we're going to go more basic. If we increase the concentration of the acid, then it's going to give off more hydrogen, and we're going to go more acidic, or we're going to have a lower pH. Okay, we have here, which concentration pH is equal to pKa? We talked about that when the conjugate acid and the conjugate base are equal to each other. Sorry, the weak acid and the conjugate base are equal to each other. Misspoke there. Give examples of some important buffer systems. We gave those examples a little bit ago, that bicarbonate and the phosphate buffer system and the hemoglobin buffer system. On to some of the more organic chemistry. Functional groups. I know everybody loves functional groups, right? Everybody loves them. So a functional group, it's an atom or a specific group of atoms within a molecule that has similar chemical properties whenever it appears in different compounds. So literally what a functional group is telling us is how that specific compound is going to interact with its surroundings. So we have a whole bunch of different functional groups. So our methyl, ethyl, phenol, hydroxyl, acyl, phosphoryl or phosphatate, phosphoanhydride, thioester, sulfhydryl, aldehyde, keto, carboxyl, ether, ester, primary amine, secondary amine, tertiary amine. There's a whole bunch of these. The thing to understand right now is he kind of he'll sometimes say in class that he wants you to memorize these, but to be blunt, ain't nobody got time for that. So what I would recommend is learning the ones that continuously pop up. Okay. For example, I'll highlight the ones that frequently pop up. Methyl is a big one. The carboxylate pops up a lot. Hydroxyl, aka the alcohol, pops up a lot. Ester will come and go, will pop up a bit. The amine ones, the amine groups, specifically the primary amine group, when we talk about proteins and everything, those will pop up. Thioester will occasionally pop up, as well as wherever phosphate, this one, phosphate. These are the main ones that will pop up. And you don't need to spend all of this time memorizing or figuring out how to draw them out and all of that. That's not realistic to understand and know all of those, okay? You want to start to do is, the more that these pop up, you just want to start recognizing the names and recognizing some of what makes them up. It's these ones that are highlighted, like I said, these are the main ones that you'll see kind of over and over again. He'll also pop in acetyl a decent amount as well. And really, this is just kind of going to be kind of practice. Again, you don't need to memorize the whole shape of everything, but I'd start recognizing the key factors of what's inside of it. It's like amine groups. Amines contain nitrogen. The carboxylate group, it's COO is the main thing. The COO is what you want to remember. Hydroxyl is the OH. Methyl is the CH3. Start to learn those, just that one specific piece. Quizlet can be really good for this. Quizlet is good for testing. Do it once or twice a day if you can for like a week or two, and then come back to it every now and then, especially right before an exam, and that'll help. For right now, the reason why he wants you to kind of learn a lot of these now is because, one, to be frank, your part 1 board exams will randomly sprinkle questions of these in to the actual board exams, which is really annoying. And 2, these all are going to play a part in different types of bonds and reactions that we're going to learn in this trimester for biochem and next trimester for biochem 2, as well as for physiology, and continuing forward from there. A lot of our pathology courses will come back to this sort of stuff, and that's why he wants us to understand these and to know them decently well. I heard somebody unmute. Does somebody have a question? Okay. Hopefully that clears up a little bit of the confusion kind of what to know about the functional groups and what they're all about. Okay.
These questions are from the book, right?
Yes, all
Okay.
these questions, everything that I'm going through is in the book. I'm skipping over a couple of them because a lot of them kind of repeat each other.
Mm-hmm.
So like as you go through them, I'd recommend like go through and read back through these and like see if you can answer them. The ultimate test of knowledge is, can you put this into your own words, and can you explain this and teach this to somebody else? That's honestly the best way to learn, is if you can teach something like this to somebody else and have them understand it, you're going to have a really good grip on the material. So if you're living with a roommate or a sibling or a parent or somebody, significant other, who maybe isn't deep into the science world, this might be something that, you can try to explain them, and they're going to come at you with like, well, why is this? Or like, wait, what about this? Or that doesn't make any sense like this. And it forces you to then like, oh, wait, yeah, what I said doesn't make sense. How do I actually word that? What does that actually mean? And if you can put it in your own words, rather than just like a random definition you pulled off of the internet, tweak it to your own understanding, you're going to be you're going to be able to actually apply that information a lot easier. Okay. We have elements and cellular architecture of the living organism. Well, okay. And this is where some of these questions, I'm going to be completely honest, we're going to Google the crap out of them and try and figure them out. It has been who knows how long since my last like general biology course. Let's take a look what the mighty internet says. Here we go. Carbon, nitrogen, oxygen, hydrogen, phosphorus, calcium, potassium, and sulfur. Isn't Google great? Now looking at these, remember earlier when we went on the periodic table and I circled those specific components? Look here. Carbon is circled nitrogen, oxygen, hydrogen, phosphorus, calcium, potassium, sulfur. Every single one up here, 98% of the dry weight of living cells, we have circled up here because these are literally the ones that we're going to be talking about because this is biochemistry. So we're talking about the biology. And if 98% of our stuff is made up of all of this, that's what we care about. It's cool how it all connects. It's as if I know what I'm talking about sometimes. Okay. Next part, draw a schematic diagram of a eukaryotic cell showing its principal organelles. This is where it's really going to combine with cells and tissues. And he has in the book this drawing right here, which not only gives you the name of every single thing, but it also tells you what it does, which is very, very, very helpful. I personally would make sure that I read through this entire thing because this trimester, especially, we're going to really focus on the nucleus, the nucleolus, the nuclear envelope, a little bit of the ribosomes, the rough ER, the mitochondria, plasma membranes are the ones we're going to focus on throughout this entire trimester. We'll have a whole chapter essentially on ribosomes and the rough ER when we talk about protein development, nuclear envelope, the nucleus and the nucleolus. We'll talk about when we talk about, again, protein development, DNA synthesis, RNA, mRNA, tRNA, all that good stuff. Mitochondria, when we talk about we'll talk about glycolysis and the Krebs cycle and the electron transport chain, which is how we produce ATP, how we produce energy for the entire body to continue living. So yeah, if you understand already what the function of each of these is, it'll be a little bit easier to understand later on when we start getting into all of them. Okay. And that is the whole part for the elements and cellular architecture of the living organism. Any questions up to this point? Ooh. I need a snack. Okay, we're down to the last 10 questions. We have what is formed when an alcohol is oxidized. Did I miss a section? I feel like I did. Maybe it's later on. Because I was reading these questions before we started. And okay, that's why. I'm going to actually rearrange some of these questions because I think they're in a stupid order. Define oxidation and define reduction reactions.
Did you already talk about the osmosis and osmolarity?
Was that in these questions? I didn't see it.
That's the only thing I have on my notes that I don't think we talked about really. Osmotic pressure and osmosis and all of that.
Okay. Let's do that real quick before we jump into the organic chemistry stuff. Let me actually pull open. I don't know why this is covered in Physiology 1 later, but okay. This is actually material from Physiology 1 that you'll have next try, but it correlates exactly with all this. So you have diffusion and you have osmosis. Specifically, osmosis is movement of the water across a semi-permeable membrane to the area of higher solute concentration. So this is exactly what we just talked about. I told you this would come back to haunt you. Isotonic, hypotonic, and hypertonic solutions. The movement of water specifically is osmosis. And the way that that happens, that it's able to happen, is because all of our membranes, especially like our main cellular membranes, is a phospholipid bilayer that allows this transfer of water to go through. And essentially, water is going to flow to wherever the concentration is the highest. That is osmosis. When we talk about osmotic pressure, find osmotic pressure is defined as the minimum pressure that must be applied to a solution to stop the flow of solvent molecules. So it's talking about solvent, we're talking about the liquid, we're talking about the water, through a semi-permeable membrane. So we have this membrane, and we're going to add pressure here. So typically, if we have a semi-permeable membrane right here, and we have a very high concentration of solutes of stuff mixed into here, all of the water is going to want to rush into it. But if you apply pressure to it, this is known as the osmotic pressure. However much pressure you apply is going to, that pressure kind of cancels out the water's ability to flow across the membrane. And that's what an osmotic pressure is. You won't really get a lot of questions about osmotic pressure. You'll talk a little bit more about osmotic pressure, mostly in physiology courses. It just has to do with the flow of water back and forth between between the cell, between the cell membrane. Do you have another specific question about that, or is there another kind of chunk of it that he talks about that?
No, you just mentioned that you might have missed something. That's the only thing I saw that we didn't go over.
Okay. Cool. Yeah, you'll get a lot more into that next trimester in physiology. So yeah, Dr. Sarkar does a really, really good job of introducing concepts that you will see later on in the program. He's really, really good at that. Typically, you don't notice that until you come back and re-look over this material, which I have looked over it quite a bit now, and it's really, really cool. If you put the time and the effort into Dr. Sarkar's class, you will be much further ahead than a lot of people in your future classes. Like I promise you that you will be leaps and bounds ahead of people if you put the effort into this class, which you're all here, which means you're putting the effort in, which is awesome. Okay, oxidation reduction reactions. You are going to get sick and tired of him talking about oxidation reduction reactions because they are everywhere. The thing to remember about oxidation reduction reactions is oil rig. Oxidation is gain. Sorry. Oxidation is loss of electrons. And reduction is gain of electrons. Okay. There's a little bit more into it. So it's like, or it can be gaining oxygen. And often the loss or gain of electrons is accompanied by a hydrogen atom. So oxidation is loss of electrons / hydrogen. It's gain of electrons / hydrogen. And you'll talk a lot more about oxidation reduction reactions and exactly like what reactions they are and all that sort of stuff in quite a few different chapters because they're very, very common in the body for a lot of the different just processes that we typically have. That's as far as I want to go right now. Have you guys talked much about oxidation reduction reactions yet? In like in the actual class?
Not much, no.
Okay. Okay. I'm not gonna go too much deeper. This is probably going to be the material, the oxidation reduction stuff. If I'm not mistaken, it might even be this week that you guys cover a lot of that. Let me see. Amino acids, proteins, enzymes. You guys just had week 2, right? Going over amino acids.
Yeah.
Yeah, I don't think you'll start to get into a lot of the oxidation reduction reactions in chapter 4. So probably in the next 2-ish weeks or so, you'll get into oxidation reduction reactions. So yeah, I'm just gonna give you the little introduction.
I think I missed the oral rig connection. Can you explain that again? What was that?
It's just a little mnemonic to remember.
Okay.
Oil rig, oxidation is loss, reduction is gain, specifically of electrons. Yeah.
Gotcha.
Mnemonics are a really, really great way to remember a lot of this stuff. If you watch my YouTube videos, when I did my part 1 board reviews with Irene Gold, they gave a lot of different mnemonics. And so I try and jump back and forth in those videos to those mnemonic devices, just like little phrases or sayings or stuff like that to help remember the order of certain things or just like little memory tricks. I try and include as many of those as I can remember in the videos that I recorded. Okay. So now we get into this next part, which is this whole next chunk, honestly, is kind of just going to be memorization. He likes to ask questions about this. I personally have not really drawn the connection through all of this stuff, but I just know that he really, really likes it. And yeah. So we understand that the oxidation is going to be loss of electrons, so removing of the hydrogen. And this covers the next kind of chunk of questions in the book. So for example, what is formed when an alcohol is oxidized? Primary alcohols are oxidized to something called aldehydes. What is formed when an aldehyde or ketone is oxidized? So the aldehydes or ketones are oxidized to what's called carboxylic acids. What is formed when carboxylic acid is reduced? This is a good thing to remember. Oxidation and reduction are opposite of each other. So if I were to say, if I oxidize an alcohol, I get an aldehyde. If I reduce an aldehyde, I then get an alcohol. So it's going back and forth between them is what oxidation and reduction reactions are. So when carboxylic acid is reduced, you get aldehydes. When an aldehyde or ketone is reduced, the aldehydes or ketones are reduced back to primary alcohols, and so on. You could write this a whole bunch of different ways. He really, really likes questions for coming from this stuff, where he'll literally ask these exact same questions. Like, what is formed when an aldehyde or ketone is oxidized? Like, he'll ask that exact same question. So you really just kind of need to memorize this chunk of stuff. I would memorize it like this. Alcohol goes to aldehyde, goes to carboxylic acid. Then this is all oxidation. And then reduction, it's going to literally be opposite. Carboxylic acid goes to aldehyde, goes to alcohol. And then do the same thing, like throw in there instead of, and like secondary alcohols go to ketone. So do it again. So alcohol, I would do primary, secondary, and so on like this. And I literally just review this 5 or 6 times so that you know it forwards and backwards, because he'll throw a lot of these questions at you. And they were always my least favorite. I always hated these questions because I honestly didn't do exactly what I'm showing you to do right here, which is why I'm telling you to do it, because he'll throw a lot of these at you, and they should be easy points if you understand just this straightforward back and forth.
Do we need to know the difference between primary and secondary alcohol?
I mean, I don't know the difference, so maybe. Let's find out. Primary alcohol is an organic compound in which the carbon atom that carries the OH group, there's our functional group, our alcohol functional group, is only attached to one alkyl group, whereas secondary alcohol is an organic compound in which the carbon atoms that carry the OH group attach to 2 alkyl groups. Cool. So this is what it looks like. Oh, that makes sense. Primary alcohol has 1 OH, secondary has 2, tertiary is going to have 3. Huh. That would have been nice to know 2.5 years ago. Probably not overly important, but again, let's actually a little tidbit here. So if it does come up and you're able to draw a connection from this, more power to you. Okay. What is formed when the hydroxyl group of an alcohol reacts with the carboxylic acid group of an organic acid? That's a good question. To be honest, I think at this point, I think we're going to stop this here, because a lot of this you guys haven't covered yet at all. So, and this is just going to be me kind of explaining a lot of other, there's a lot of stuff in between what is the oxidation reduction reactions and like the actual thioester bonds and the cleavage and that sort of stuff. That's not until you guys get to enzymes. So I'm gonna actually go ahead and stop here, because I feel like adding these might just be a little bit more confusing until you get to that point. That wasn't too bad. About 3 hours, just like I planned. How's everybody doing?
A little overwhelmed, but we'll get there.
It's a lot, but I think that the most important thing is repetition. If you can see the concepts enough and see them more and more times in different ways, it's easier to get them to stick and to be able to understand them.
Besides the book, do you know where we can get like more good practice questions?
ChatGTP.
Chat GTP.
It's an AI generator. And literally go into here and like, if there's a subject you want to practice, like give me practice questions about oxidation, reduction, reactions. And you can make it so it'll literally give you questions. And some of them, like you can go through them and some of them be like, what? And so then feel free to ask for explanations or answers to any specific question you're unsure about. So like you can copy paste. Answer this. And it'll walk you through the whole thing. Or you can make it more simple and do give me multiple choice practice test on oxidation, reduction, reactions. And it'll generate multiple choice questions.
That's crazy.
Yeah. I used to write, like when I was tutoring and stuff, I'd write practice questions by hand and had to make them all up. And yeah, that's like a long time. I wish I figured this out last trimester. Yeah. So the big thing to remember with this, you can do this with any of your subjects on campus, as well as like any subject within a specific class to give you practice questions and to help you understand certain things. Two things to understand. One, some of these questions might not be directly related to what you have learned. For example, like this stuff is asking about the oxidation state of hydrogen in most compounds. That's something like if you have never heard of oxidation state before and you have like watched all of the lecture videos and read the book and done whatever, if you've never heard of it, don't get hung up on it. Okay, I cannot emphasize that enough. If you have no clue what that is talking about, if you want to know, do a quick Google search. If it takes you more than 5 minutes, come back and realize that it's probably not important. Okay, but stuff like this, reducing agent, and when you start to talk about these, you'll get a lot more into this reducing agent, like what a reducing agent is and what it actually does, and what the purpose of a reducing agent is. Okay, it's like this kind of question, great question, and he will ask questions just like this. Maybe not these exact same, probably not this exact same equation, but something similar. So if you understand the concept behind it, then you can answer the question. Oxidizing agent in the following reaction, he'll ask a question exactly like that. Which of the following elements undergoes reduction in the reaction? He'll ask a question similar to that. This is asking about balanced half reaction. We don't do balancing and stuff in this. From what I remember, we don't do any balancing of equations in this class. So like this one, just cross it out and skip it.
Will they give us the correct answers?
Yep, the answers are down here below.
Oh, perfect.
Yeah. Love ChatGTP. You can also use ChatGTP. I literally have used this for a whole bunch of different stuff. Like right now in clinic, like I have, if there's like a specific case and I'm not sure about something, you can literally throw in here, like, write me a strategy to approach this specific issue with the body. And it'll give you a bunch of ideas. And then you can read through them and based off of your own knowledge, apply them. Or like if you have, but even if you have like questions about studying and stuff, like I'm struggling with this, like, or if you're struggling with sleep, let's say, throw into ChatGTP, what are some of the most evidence-based ways to help me fall asleep faster, or to help me sleep better? And it will spit out research articles and stuff at you and give you examples of what you need to do. Like you can literally use it for like this. Literally, the sky's the limit with it. So do not, and I repeat, do not use it to cheat, because I promise you, first of all, don't cheat. It's not worth it. Before I was before this trimester, for the past year, I was the student body vice president, and I had to sit in on disciplinary hearings for students, and I had to vote to kick them out of school, and that is not fun. Okay? We do not want to be doing that. This is biochemistry. Let me save this. Chapter 1, review questions, material. Okay, at this time, any last questions, thoughts, concerns, anything else?
I was starting to get pretty spacey just because of my own study style, you know, how I work at night. But I'm really glad you did this at the same time, and I appreciate your time. We'll probably come back and look at the end of this.
Definitely. You lost me about 30 minutes ago, but I'm trying to.
I get you. Don't worry. It gets easier. Well, it gets easier in ways. Try 1 is difficult because because you're essentially doubling the amount of credits that you typically would take in an undergrad program. And it's a whole new beast. Try 2 is difficult for its own reasons. Typically, try 3 is a little bit of a breath. Try 4, again, kind of brutal. Try 5 has its own challenges, but it's a lot less lecture, it's a lot more hands-on, and so on. And you learn to start to manage the stress, and you start to manage everything. Just again, I do recommend this to everybody because not a lot of people know about this. There is an option within this specific program, to take a reduced load schedule. And I do not recommend that everybody does it at all. It's something but I want everybody to know that it is there as a potential option, and you can go and talk to administration about that. And know that administration and the teachers and the other students and everybody here at Parker is trying to help you succeed. Whether it always seems that way or not, I promise you, they want you to succeed. And something like if you are truly, really, really struggling, especially if you already have any mental health issues, and you get to a point where you have depression type tendencies, or you have severe anxiety, or you're having any like really bad thoughts, do not let school ruin your life. Okay, there are so many options, so many people to help. I promise you that you'll get through it. You'll get through the program as long as you keep yourself mentally and physically okay as you can be. There's going to be stress. There's going to be a lot of headaches and a lot of stuff going on, but just keep track of yourself. And again, like if anybody ever needs anything, feel free to reach out to me. I try to be good at responding to group me and to texts. I promise I'm not trying to ignore anybody if anybody has reached out. And yeah, I'm just going to end my rant there.
For the reduced course load, do we get to like pick and choose when we do that? Or if we go, we have to continue that throughout the whole process?
You can like
can we go by tries?
You potentially can. It just depends on which classes you have. You'd have to talk to administration about that and figure out, first of all, if it's even an option for you, just because of like the way federal funding and student loans and all that sort of stuff works. There's a whole bunch more behind it. So you have to figure out, first of all, if you're able to do it. and then also kind of what that whole process looks like. It's more just, it's one of those options where I've known of a couple of people who just were really, really struggling mentally and physically to the point of like wanting to drop out. And that is like, hey, this is an option for you. You do it. I recommend, if you can do the regular course load, do it, because you'll stay with your try. You'll know everybody, and you'll be able to keep pushing through, and it'll be awesome. But if you can't, there's all sorts of options and remedies for you to be able to make it through the program, even if it's not on the same exact track as everybody else. Okay. Okay, everybody. My baby just woke up, and I think he's hungry, so I am going to log off. Thank you so much for coming, for being here, for participating, and I hope you all have a great night and a good, relaxing Sunday.
Thank you so much for your time, and I hope your baby goes back to sleep very, very fast.
Me too. Have a good night, everybody.
You as well. Thank you.